Good afternoon again. Hi everyone. We're going to get stuck into the last part of today, which is shortest path, and then just briefly talking about assignment 2. The purpose of talking about shortest path algorithms is, well, I mean, most of you should probably have an intuitive sense that finding the shortest path between two things is probably a really useful thing in general in life. It's one of the main reasons we use graphs. You, every time you type into Google Maps how to get from A to B is a derivative of that. There's so much in your life that if you really thought about it would involve shortest path algorithms through something that could be represented like a graph. So really cool. Why we talk about shortest path though as a separate topic is all to do with edge weights, and I really want to stress this because a breadth first search that we learned about in week 5, where you just move out from a graph in every direction, that gets you the shortest path, right? Like we talked about that. So if you have a graph, your BFS will get you the shortest path. It'll find the right way if you use BFS for pathfinding under one condition, and that is that all of your edges have uniform weights. So a standard breadth first search is a shortest path algorithm when it comes to uniformly weighted graphs. It doesn't need to have no weights, they just need to be uniformly weighted, where the cost of a step is equivalent regardless of which step you take. So the point of talking about stuff today, edge relaxation, Dijkstra's algorithm, is that if your graph has edge weights, a breadth first search is a little bit too simplified. And we need to have a slightly more, I guess, in-depth understanding of what we're doing. I've just kind of said this already, sorry. Formally, a shortest path is a type of search that looks for two vertices, a path, a linear line between two vertices on a weighted graph with non-negative edges. Now, I think this concept isn't the easiest one to grasp, though it's definitely not the hardest, is that in different languages, you would tackle a shortest path problem differently. In languages like Java or object-based languages, you would probably just you would create your own types, basically. You create some classes and objects to do this stuff for you. Because C is a primitive, low-level language with very limited abstractions, we have to do this kind of slightly differently at how you might have done it if you've done it in another language. And I just want to point this out because both if you've solved like a Dijkstra algorithm or what we're about to do today in a higher level language, a shortest path thing, it's likely that you can't translate a ton of that knowledge. And similarly, when you learn it in this course and then you come across it in other courses, you can't, I would not recommend that you do this because this is how you do things in C. And any kind of language with objects, you'll do this very differently in. But to take a real snapshot of what we're dealing with here, if we have a graph like this one, this is a digraph with edge weight. So it's a directed graph that has weighted edges. Typically, what we will do is we will use two arrays, where the arrays are the length based on the number of vertices. So there's 5 vertices, array of length 5. We'll use 2 of them, and what these arrays will represent is information pertaining to the shortest path from a starting point. So all the data structures we need to find the shortest path in any kind of graph from a node, that's the specific part, is these 2 arrays. And if you need to find the shortest path between every node, but like what's the shortest path from this node to every node, this node to every node, that node to every node, you need sets of 2 arrays. And I just want to make that point clear. So it's like, this is all the data we need to learn what the shortest path is from a specific node. So you always need that specific node. And if we were to pick another starting node, all this data would be different, or we need to kind of, handle data separately. Now we have these 2 arrays, these 2 v-indexed arrays, because it's the number of vertices. And the top array dist is the distance. It's essentially saying, this is the cost of the shortest path that we found from the starting point, what this entire two little arrays is about, to a particular vertex. So what this table here actually says is from vertex 0 to vertex 0, the distance is 0. The shortest distance is 0. From vertex 0 to vertex 1, the shortest distance is 0.3. From vertex 0 to vertex 2, the shortest distance is 0.7. Vertex 0 to vertex 3, it's 1.1. And vertex 0 to vertex 4, it's infinity because we can't get there. Or like -1. It depends on what your implementation is. It's basically saying not possible. And that makes sense because the in degree of vertex 4 is 0. There's no way to get to it. Therefore, there's no way to meaningfully determine what the shortest path to it is. Pred is short for predecessor, which means that how did we get here? So for the shortest path, how did I get to this node? So the way I'll explain it, therefore, is that if you can build out this array, which is what the rest of this lecture is about, and therefore what you can say is, okay, if I want to, what's the shortest path from 0 to 3? How long is that path? The answer is 1.1. It's 1.1 cost to get there. How did we get to the 3? We got to the 3 via the 2. So this predecessor array, all the indexes line up, and it simply tells us how did we get to the 3? We got to the 3 via the 2. Okay, well the 2, how did we get to the 2? We got to the 2 via the 0 here. So this actually tells the story of how you get to each one. So Autumnal says, is it the immediate predecessor or a list of predecessors? It's the immediate predecessor in this case. And that just means it has 1. So it's like in this graph here, if I want to figure out what the shortest path to 0 is, then, sorry, if I'm at 0 and I want to figure out what the shortest path to 1 is, I can just look it up in this graph. It's 0.3, that's the shortest path, and 1 came from 0. Okay. What is the shortest path from 0 to 2? Well, it's 0.7 and 2 came from 0. Okay, sure. Shortest path to 3 is 1.1 and we came from 2 and 2 came from 0. Okay, so I know I go 0, 2, 3. It's a little bit like how we did that pathfinding stuff with the searching algorithms. And then similarly, if we wanted to do a different shortest path data set where 4 is the starting point, we could fill it in like this. So if we wanted to say what's the shortest path from 4 to 0, it's 1.3. And to get to 0, we have to go from 3. To get from 3, we have to go from 2. And then to get to 2, we have to go from 4. So you can actually build the path out backwards. So therefore, I could tell, okay, well, if I want to get to 0 the shortest way, if I work backwards, it's 0, 3, 2, 4. And therefore, I know it's 4, 2, 3, 0. That makes sense? 4, 2, 3, 0. This is the data structure that we work with as part of this shortest path algorithm, Dijkstra. The real question here, though, is how in the hell did those numbers get populated, right? We've got these tables, which are very informative. It tells us the shortest distance, tells us what the predecessor was, but it's not telling us, how do we generate this? Like, this didn't just come out of thin air, did it? We actually had to make it. And that's really what we're going to be talking about. So how we make it is by using, we're going to talk about Dijkstra's algorithm. How we make it is with Dijkstra's algorithm, but before we do that, we want to understand a really important key conceptual point, which is what we call edge relaxation. And the way edge relaxation works is that if we, let's say, how to explain this? So when it comes to building out this table, and in fact, again, these are the first times I teach these things, so sometimes I'm like, oh, maybe I'll do this slightly differently. But when we're building out this table, it's a little bit more complicated than just filling in the values. In fact, what you actually do is the table starts off with a set of values, and then you start exploring the graph. And every time you explore the graph more, you sometimes have to update and reset these values. So it's like an ongoing process of actually filling in this table as you explore the entire graph. It's not just like, there's a formula to fill it in. You actually have to search the graph, and as you search the graph, you might update those values. When we update those values as we search it, that's what we refer to as edge relaxation. Oops, sorry. That's what we refer to as edge relaxation. And I think this is one of those things that you should go and try and read once you get the concept, because I don't think it makes a lot of sense just reading it. But essentially what it's saying is that when we're exploring a graph, sometimes we might find a faster way to get there. Now, this is actually really obvious here in the case of, like, say I'm trying to find the shortest path from 4 to everywhere else in the graph. Okay? Well, let's say that 4 looks at 2 and it looks at 3. It thinks at this point in time, in exploring, that the shortest path from 4 to 3 is 0.9. Right? But as we keep exploring, as we explore 2, we'll actually find that actually the shortest path from 4 to 2 to 3 is shortest path from 4 to 3 is actually 0.5. It's via 2. Right? So there's actually, like, we're actually learning as we go. And I think that's a really important notion to get in your head, is that finding the shortest path and filling in this table is like an ongoing learning process until you've actually searched the entire graph. And that learning process and kind of revising what you think is the shortest path is what we call edge relaxation. I won't go through the logic of it here, but like another example here is that, let's say we're exploring this graph here, and we haven't explored green yet, but we've explored the red line and the blue line. And what we found out so far is that from S, the shortest distance to V is 8. Okay? And its predecessor is this little blue thing here. From S, the shortest path to W is 12. And its predecessor is this little line here. So at this point in time, we think that the shortest path from S to W is 12, and it's via this line here. It's via this predecessor. But as we keep exploring the graph, and we keep exploring, and now we explore from V to W, suddenly we realize, holy crap, there's actually a shorter path from S to W, and it's via V. And its total length is 11. So now, previously W, the distance to W was 12, and it came from this little dot here. But after we've learned more by exploring the graph, W has a distance of 11, and its predecessor is V. So we actually learn more. So this is what edge relaxation is. It's basically the process of, like, ongoing learning of what the shortest path is while we're exploring a graph. But that kind of leaves the question, how do we explore the graph? And this is where pretty much the rest of this lecture is about Dijkstra's algorithm. So Dijkstra's algorithm... So Blake says, why is pred V unknown? Look, I mean, these slides, some of these slides are copied, but the predecessor of V is in this in both examples, is actually this little dot here, because it's the one immediately before it. I think whoever made this diagram decided to not label it and just put question mark there, which I think is a bit confusing. But essentially, it's this dot here. And in this particular left half of the diagram, the predecessor of W is this dot here. That's why they come up as question mark. It's not because they're not known, it's just they're not defined on the graph. It's a bit weird. I when I was looking at this, I was like, what the? But then I got it. So that's a great question. So with Dijkstra, the easiest way to think about Dijkstra is that it's kind of like a breadth first search. If you come at this saying that conceptually it's going to be something that starts at a point and it expands outwards in a specific direction, then you're kind of halfway there to conceptualizing it, because that's essentially what it is. Now, this pseudocode won't make a ton of sense to start. So let's actually run through an example and then we can maybe loop back to it. So this example here is us trying to figure out what the shortest path is from 0 to all other vertices in the graph. Because remember that when we have these two arrays to Dijkstra, it's all about finding the shortest path from one node to any other node. And if you want to find out the shortest path from any node to any other node, you have to apply Dijkstra v times, right? You have to run this algorithm for each starting point. But it's always one starting point and all the endpoints. So this is my graph, 0, 1, 2, 3, 4, 5. We got 6 nodes. Therefore, our distance and our predecessor arrays have 6 elements in them, 6 elements in the array, 0, 1, 2, 3, 4, 5. And when we start this algorithm, we set all our predecessor values to be blank because we don't know what any predecessors are. And we fill in our distances with some placeholders. Now the distances here, in this case, well, the distance from 0 we know is 0. We can fill that one in immediately. Makes sense. The distance from 0, all of these tables are from 0 to something. From 0 to 1 is infinity because we haven't figured it out yet. So it's kind of like a placeholder. It's like, we don't know. Let's assume that you can't reach it. Let's assume that it takes infinite time to reach because it's not possible. Okay? Great. So that's the starting point. That's like the initialization of it. Then we start to apply a Dijkstra. And again, not getting into the pseudocode, just focusing on the rules. It's like you just explore out like a breadth first search. So one of the first things we do is we start at node 0, and then we look at the 3 immediate children, which is 14, 9, and 7. Well, sorry, the 3 children are 1, 2, and 3. So because we have 1, 2, and 3 as the children, we can go and update our table. So we can update it for index 1, index 2, and index 3, because as we're exploring, we've learned something now about what the shortest path is from 0 to 1, 0 to 2, and 0 to 3. We might keep learning more, but we've learned something, so we have to update the table. We update 1 to be 14, 2 to be 9, and 3 to be 7. That makes sense, because we now know, to the best of our knowledge currently, that the shortest path from 0 to 1 is 14. And the shortest path from 0 to 2 is 9. And the shortest path from 0 to 3 is 7. So we've got those in our table. The other thing we have to do is fill in the predecessor value, which is where we came from. So how did we get to 1? How did we get to 2? How did we get to 3? Well, that's easy. We all came from 0, which is our starting node. So we just fill in that those little particular indexes of these arrays. Conceptually, that's not the weirdest thing in the world. You know, it's just a process. Then the next question is, okay, well, which node do I explore next? Do I explore 1, 2, or 3? I've already explored 0. And as far as you're concerned at this point, the graph doesn't really exist. Like, the graph is like, as far as the search algorithm's concerned, I'm just dragging this off the screen. Oh, I can't. Can I? Oops. Yeah, as far as the search algorithm's concerned, that's like all we can see, right? We don't know what's beyond that. We only know the 0, 1, 2, and 3. We've already explored 0, so we have to pick which one to explore next. And it's like, which one? Well, the rule we follow is that we pretty much explore from the shortest, the node that has the shortest path currently. And that makes sense. Like if you're trying to find the shortest path in a graph, you might as well explore it along the cheapest route. So out of this 1, 2, and 3 node, the next vertice that we iterate on is 3. V equals 3, because it has this really short path here. So we do exactly what we did before. We look at 3's children. Now what children does it have? It has 2 and 5. They're the 2 nodes. So 5's really simple. We look at 5 here and we add it. The distance to 5 is 7 plus 15. It's not 15. One of those, pay attention here. It's not 15, it's 7 plus 15, because it's like the cumulative. So, you know, what do we know about the vertice 5 here? Well, we got to it via 3. And 3, we got to, which costs 7. So, like, all the data's here inside the table. Like, you know that to get from 0 to 3, it costs us 7. And then there's going to be another 15 to get to 5. So that's why it becomes 22. Because remember, these tables are always reflective of the shortest path from the same vertex. This table, this table, this table, the ones on the next slide, these are all about the shortest path from 0 to a vertex. So it is 22, because you've got to go 7 and then 15. When we add the 2 here, what we notice is that it's actually already in our table. We already have, we already have a second, we already have a 2 index in our table, right? And it says the cost of getting there was 9. Okay. So when we are expanding and exploring out of 3, we see there's a 2 here. And we go, okay, there's a 2. However, what we notice is that the 7 plus the 10 is 17, and we've already found a shorter path. There's already a shorter path to 2, and it costs 9. So our other path we found of 17 gets like disregarded because there's already a shorter path. We haven't learned anything new, right? Like even though we found another path there, it's not better. So there's no new information about the shortest path to 2. So in the chat, yeah, Naoki's saying, why is 0 to 5 not 12? You know, and clearly Naoki's looking at 0 to 2 to 5. And yeah, people have already answered this, but basically it's just because this algorithm, even though to you it happens instantly because you just run it on the computer, it still has to explore things in a really methodical way. And what we're taking you through here is actually the processes involved with how it comes to that conclusion that's inevitable. So this is our new dist and pred arrays down here. They've been updated. The next slide, sorry, just quickly, how do we know what to explore next? You know, we've got 0, 1, 2, 3, and 5. Well, we've already explored 0 and we've already explored 3. We can't explore those again, so we're going to have to explore the next lowest, shortest path, which is 2 in this case. Because to get from 0 to 1 is 14, 0 to 5 is 22, 0 to 2 is 9. So it's the smallest edge of the node we've yet to explore. So 2 is the next thing that we iterate from. So in this case, we iterate from 2. And what do we find from 2? Well, 2 has 2 children, which is 1 and 5. So first thing is I'll do 1. Now what do we notice about 1 here is that the cost of getting to 1 is 13. So what we actually do now, and this is what edge relaxation is where, I don't know why, I mean I know why it's called that, but it's a curious name, is like we're relaxing the edge here, which basically is just a weird way of saying that we have found a shorter path. We found a better series of edges. So now, in this previous thing here, you saw that the distance of 1 was 14, which was saying that the shortest path between 0 and 1 is 14. Whereas what we've just found is that if you go 0 to 1, because we've just been learning outward from 2, it's actually now 13. So the process of edge relaxation is updating our table, replacing the 14 with the 13, because that's the new cheaper path. But how did we get to the 1 now? We got it to it from the 2. So that's kind of where that information is encoded, because you can't just say, oh, 1 has like 1 costs 13 to get to, but it's like, how do we get there? You can't just tell me we can do it. I need to know how we get there. And in this case, it's saying, oh, I came from 2. Okay, so the total distance from 0 to 1 is 13, and the predecessor of how to get there at the end is 2. So therefore you can go, okay, from 1 to 1 I came from 2, 2 I came from 0, and there's your path, right? So we're still learning, but that's just one of the children of 2. The other child of 2 here is 5. So a similar thing. We say, okay, well, 0 to 5, 9 plus 3 is 12. We look at our current table, which was this one, and we say, oh, wow, 12 is a lot cheaper than 22. We better do some edge relaxation here and reduce it down to 12. And because we've changed how we got there, I'm going to have to update the predecessor too. So in the previous example, the predecessor was 3 because we went 0, 3, 5. But now the predecessor is 2 because we went 0, 2, 5. Right, like that. Same process again. We've now explored vertex 0, vertex 2, vertex 3. We've got 3 vertexes left. One of them's infinity, one of them's 13, and one of them's 12. So the next vertex we explore is 5. Okay, and 5 has one child, which is 4. So we haven't explored 4 yet, so the distance to 4 is 0 to 2 to 5 to 4, which is 9 plus 3 plus 8, which is 20. So we populate this one with 20, and we got to 4 via 5, so we put the predecessor here as 5. Great. We got 2 vertices left to explore, which is 1 and 4. 1 is smaller than 4 in terms of distance from the starting point. So we explore 1. 1 has one child, which is 4. The cost there is 14 plus... Is there a typo in this? Oh, no. Oh, no, I just got confused. See, this is me being typo in my brain. So like, here's the funny thing, right? This is why the predecessor list really matters, because if I say to myself, okay, what's the total distance to get from 0 to 5? and I'm via 1 at the moment, I actually need to look at my current table to figure out how I got there. So it's like, okay, well, 1 to 4 cost me 5. But how did I get to 1? What's the current best way to get to 1? Well, I look up my table. The predecessor of 1 is 2. Okay, so I came via 2. Okay, so that's 4 plus 5 is my weight. Well, what's the quickest way to get... Like, how did I get to 2? What was the predecessor there? Predecessor was 0. Okay, so now I know what the fastest way is. So that's 9 plus 4 plus 5, which gives me 18. Now, 18 is cheaper than the previous value we've had for 4 here. Because previously we thought we would go, 0, 2, 5, 4, like that. But we've now found a cheaper way. So we've had to relax that edge again and update its predecessor. Okay, so we've done all that. And then the very last node to explore is 4. This last vertex here. Except it has no children, so there's nothing to do. And then we finish our table. So back at the start, when we started this topic, I was like, oh, we have to figure out how to generate that table. Now, from this table, you can find out everything. You can find out the shortest path from 0 to any other vertex here. Generating that table comes from using Dijkstra's algorithm. And once you've finished everything, this is now your table. This tells you all the information you need to know. It tells you what the shortest path is to every node, what the cost is, and in each case, what its predecessor is, which you can use to build a path there if you need to build a path there. Now, the complexity of Dijkstra is relatively simple to figure out. Each edge needs to be considered once. That makes sense, because like in the exploring of it, we had to go through every edge at least once. And the outer loop has v iterations. Okay, sure. So I'm just reading the chat. Oh yeah. And the outer loop has v iterations. Now that makes sense, because when we talk about this, it's like the outer loop, we have 6 vertices and we had to do 6 runs of Dijkstra. So there's an outer loop of v. And then we have to consider each edge at least once. Now, the next part is implementing find all of the find all of the vertices in the vertice set with minimum distance. This gets a bit weird. So it's like, if you want to use Dijkstra's to figure out all the shortest paths, then you have to do that for v as well. So I guess what I'm getting at here is like, if we have to go through all the edges once and define the shortest path from 0 to somewhere else, it costs us v. To then find the shortest path of all edges, we then have to do that v times, and that's where we get left with v squared. A little bit weird. It's not vital that makes perfect sense, because we can come back to this stuff next week and when we talk about the assignment and revision and stuff. But probably just a key thing to note here is that e plus v squared gets simplified to v squared, and that's because we know that a property of a graph is that e is always less than v squared. Because a vertice can have at most v minus 1 edges. The most edges you can have in a graph is where each vertice has v, I think it's v minus 1, is it? Yeah, where for all v vertices, they all have v minus 1 edges. That's a complete graph. So v minus 1 is v squared minus v, which is less than v squared, so therefore we know that e is less than v squared. I'm not a mathematician, and this makes sense to me, so I'm hoping for the best. But anyway, the point is, because we know e is less than v squared, we can consider this component here to have a lower value than this component. Do you know what I mean? Because even if e was v squared, it would be 2v squared, right? Because v squared plus v squared is 2v squared. So it's basically coefficient anyway. So that's how we end up with v squared at the end here. We have to loop through all the edges. You have to, for each vertice you want to find the shortest path of, you have to loop through all the vertices. Yes. Blake says, if you add an edge, do you have to redo the whole thing, or is there a better way? Look, I've honestly never dealt with a graph where I've been like, there's probably some smart ways you could not redo the whole thing, though for all real purposes, you'd probably just redo the whole thing. Because anytime you add an edge, there's always a chance that there's a faster way, but there would be some smart ways to just redo part of it, yes. It's not something I've ever had to do, but it would definitely be possible. If I just point back to this edge relaxation slide for a sec, all this all this slide was really saying was that if I currently have a distance to W, and I suddenly notice that my distance to V plus a new weight is smaller, then I just update my distance. Basically, this whole slide is just a more formal way of saying, as we run Dijkstra, sometimes we learn a new best way to get to a node, so we have to update our table of data, right? That's the gist of that. Are there any last questions about this? Because otherwise, I will start to talk about assignment 2 for our last 15 minutes. Okay.